We didn't get to do lab yesterday, so we'll just go ahead and plan on doing that lab next week, okay? So just, you got the pre-lab done, you got everything done for lab next week already. As a reminder, we have some competencies due a week from today, right? And there's going to be a couple other competencies opening up tomorrow, right? So at this point, if we're struggling with any of them, if you haven't completed any of them, because I'm assuming all of you spent yesterday just rehashing all of the old spectroscopies and you bailed them out this morning, but you didn't have to finish them. So my assumption at this point is that we are finished with all the competencies that are posted, okay? And we're starting to work on, or we'll be ready to take conjugated systems when it opens tomorrow, okay? So by class on Friday, you will have passed 5 competencies, correct? Correct? This is yes. All right. Right, the 5th will open tomorrow. No, that's not what I said. What did I say? You will have passed it by Friday. Okay? It doesn't matter, because you're going to have it done by Friday. We're not in that habit of, we have things to do, we're going to do them the day before they're due. We're going to keep ahead this semester. We're going to stay on track. Alright? So by Friday, you're going to have how many competencies passed? 5. Yes, Brittany?
What are you opening UV viz?
Actually, they're probably the same. Conjugated systems and UV viz will probably both open. 6. You will have passed 6 competencies by Friday.
Can you prepare?
Conjugated systems.
Any other questions? Are those new glasses?
They are new glasses.
You look like an older Judge Older.
I can see you now. They're a lot bigger. But it's weird because like it actually. This is the first time since I was 18 that my prescription actually changed. But like I can actually see you guys in the back row now very well.
You're growing up.
I don't know. Well,
You're just rough, man.
yeah. Okay. So 6 competencies by Friday class, right?
6 now?
It's 6. All right. Colin, you're on board, right? 6 competencies. No, it's not a goal. That's what's going to happen. Exactly. And if you go and take them in the morning, Kenny, and you say you pass 5 of the 6, all right? What are you going to do? We're going to find me and ask, how can I do this? Or tomorrow night, what could you do between 7 and 8:30? Go to Kim Help, right? And you can pull up your competencies there and go through them and look and see which questions you missed and so on. Okay? So Caleb has access to them at Kim Help. I was say Kelby has access to them at Kim Help. And then I'll be around. I'll be in inorganic lab tomorrow afternoon, which is in the very back hallway. But come find me tomorrow afternoon. Lab? It's from like 2 to 5.
What room is it?
In the morning? By appointment. So if you email me and say, make sure you're in your office at 8, I'll be there.
Will you be in your office today?
What did I just say to do? But yeah, I can be there. I will. I will be there in the morning. But all right. Any other questions? I'm going to take off one of the, not the last lab, I think, but I'm going to take out one of the labs, yeah. all of us make, I'll bring points somewhere. You know me. There's points everywhere. Last semester we ended up with, I think all total we ended up with like 1,167 points possible in the course. So there'll be plenty of points. Don't worry. No. All right, so we've talked about double bond. We've talked about allylic systems. And now we've talked about conjugated systems. This idea of what happens when we have double bonds interacting with one another. And it's important to understand the difference between a conjugated system, an isolated system, and an accumulated system. What was accumulated system? The two double bonds are right next to each other, right? So the two pi orbitals or two pi bonds are perpendicular to one another, so they're not interacting with one another. Now, we've also mentioned, or I've talked to you guys about the words or the phrase pericyclic reaction, right? A pericyclic reaction is a reaction that takes place in a ring, right? All the electrons are flowing around in a cyclic fashion, okay? Now, an electrocyclic reaction is a specific type of a pericyclic rearrangement where the net result is we're going to convert one pi bond into a sigma bond, or we're going to convert a sigma bond into a pi bond. Now, right off the bat, I can tell you that in an electrocyclic reaction, if we could trade a pi bond for a sigma bond, that's going to be energetically downhill, because a sigma bond is a stronger bond than a pi bond. So to break the pi bond is going to take a little bit of energy. Forming a sigma bond is going to give off a whole lot of energy. Okay? Conversely, if we break the sigma to create the pi, we're going the other direction in energy. Because breaking a sigma is going to require a lot of energy. Forming the pi is only going to give off a small amount of energy. So depending which bonds we're forming or what sum of bonds we're forming is going to go a long way in determining whether we're doing an endothermic or an exothermic process. Now, the reactions can either be photochemical or thermal. Photochemical just means that they are catalyzed by a radical or light. Right? It's a radical type process. We're moving electrons from a paired state to an unpaired state. Thermal means we're going to be doing it using heat. When we do electrocyclic reactions, we're doing a cyclic process, and in that process we can either open rings, or we can close rings, or we can do nothing with rings, right? And depending on whether they're photochemical or thermal, and the number of pi electrons, they can happen either through a con-rotary system or a dis-rotary system. And we're going to have to think a little bit about what's con-rotary and dis-rotary, all right? So let me show you a couple examples of electrocyclic reactions and get an idea of what we're talking about here. On the top, we've got 1,3,5 hexatriene. All right, you see how there's 1,3,5 hexatriene. We can do a electrocyclic process here, which electrocyclic is just a pericyclic reaction where we're trading single bonds for pi bonds or pi bonds for single bonds. But we can do an electrocyclic process with these pi electrons, where we show it as these pi electrons going to form a new pi bond here. These electrons going to form a new sigma bond between these two carbons. And notice the slight difference here. In this, we have the arrow going to form the pi bond between these two. So we show the arrow going directly onto that pi bond. Here we're showing the pi electrons going to form a new sigma bond to this carbon. So we show that arrow pointed to this carbon. And then now we have this pi. So these pi electrons going to form a new pi bond there. Now, it's pericyclic. All of this is happening at once. All 6 electrons are moving at once. The net result is we form a 6-membered ring with 2 double bonds. So we start off with how many pi bonds? 3. We're ending with how many pi bonds? 2. We're starting off with how many sigma bonds? 5. We're ending with how many sigma bonds? 6. So we're trading one pi bond for one sigma bond. Do you think this would you predict this to be endothermic or exothermic? Exothermic. Right? Our prediction is going to be that this is going to give off energy. And we can see when we look at their equilibrium, the equilibrium is heavily favored to the right here. Right? All right. On the bottom, we've got 1,3-butadiene, and it's going through an electrocyclic process. We're moving these 2 electrons to form a pi bond here, and we're using these 2 electrons to form a new sigma bond between these 2 carbons. So how many pi bonds are we starting with? How many are we finishing with? How many sigma bonds are we starting with? How many are we ending with? So at first glance, our prediction is going to be that this is what type of reaction, endothermic or exothermic? Exothermic. But in this case, it's actually endothermic. Now, why would it be endothermic? Well, I'm saying why does it favor this substrate? The strength, okay? Forming a 4-membered ring with a double bond in the ring is going to create way too much angle strain and way too much steric strain. Right, so overall, that's going to eclipse the energy that we gain from switching a pi to a sigma. All right? So going from pi to sigma allows us to predict, but we know there's going to be exceptions. All right? And that's what this is showing us. Well, it's because the reason they didn't show it there in this way is because this reaction doesn't happen. All right? Now, when you have stereo or groups attached to the end carbons, and you do these electrocyclic reactions, you're going to have stereoisomers possible. All right, let's go back to this guy, 2, 4, 6 carbons. Okay, we're doing our 1, 3, 5 hexatriene. And we're going to do our electrocyclic reaction. Okay, we're moving our electrons around. We're going to move 2 to here, 2 to here, and these 2 form the new carbon bond there. Now, in this situation, though, notice we have methyl groups going down here. Are those alkenes in the E or the Z conformation? Split it down the center, this is going down, this is going up, so it's E, split the center, up, down, E. So they're both in the E conformation. So when we do this electrocyclic process, we're going to end up with 2 possibilities for our product. All right. Now, so initially we're saying, I'm going to say, here's my double bond, and this is my methyl group. All right, my pinky's a methyl. Here's my double bond, the pinky's methyl. Actually, let me switch like this so it's going in the same direction. You see what I'm talking about? Just like that. See, did you take off? All right. So, see I've got one methyl going up and one methyl going down? If I move the 2 in the same direction, see how I rotate them in the same direction? I'm going, it's called con rotary, because I'm rotating the 2 centers in the same direction. What happens to the 2 methyl groups? They're going in opposite directions, right? So we end up with something that looks like that. If we start with them like this, but we rotate them in the same direction, what do? See how they end up going in the same direction? Right? So when the rotation occurs in the same direction, right, you see how the 2 fists are rotating in the same direction? We call that con-rotary. They're moving with each other. Right? Chili con carne, chili with me. Con is with. Con-rotary, we're moving with. Okay? Disrotary is when we're moving opposite. Dis moves opposite. Okay? In this case, whether we're moving in the same direction or an opposite direction is going to be dependent upon whether we're doing the reaction with light or doing the reaction with heat. If we do the reaction with heat, we get the product from which? Disrotary or conrotary? We're doing our disrotary, right? If we do the reaction with light, what happens? We get the conrotary product. Now, take a second and think about this one for a minute. In this one, notice now we've got a methyl group. On this one, it's going up. And where is it going on this one? It's going up, right? So if I do conrotary, do I end up with cis or trans? Conrotary gives me cis. And if I do disrotary, what do I get? I get trans. So we can actually get the same two products from the different starting materials by switching between heat or light. Whereas heat with one gives us the cis, from the other it gives us the trans. Okay? So now we've got to figure out a little bit about why that is and how that expands. All right? Yeah. Okay, so let's take an example a little simpler. Just look at ethylene. All right? With ethylene, we've got two molecules, each with pi bonds. And in theory, we can do a 2 + 2 cycloaddition. All right? 2 + 2 means we're taking two atoms from one, we're taking two atoms from the other, and we're combining them together to form one ring. So if I do a 2 and a 2, how many atoms are going to be in my final ring? 4. If I do a 2 + 4 cycloaddition, how many atoms are going to be in my final ring? 6. If I do a 2 + 8 cycloaddition, how many atoms are going to be in my final ring? 10. Right? Well, here's a 2 + 2 cycloaddition. 2 + 2, 2 atoms, cycloaddition. We're adding them together to form a ring. Now, overall, how many pi bonds are in our starting material? How many in our product? How many sigma bonds in our starting material? How many in our product? 4. So, energetically, we're thinking this might be okay. What's the one hiccup in the back of our head, though? The string, right? We're trying to form a four-membered ring. Now, for this to happen, we have to think about where the electrons are and where the electrons are going. Okay? We can't just have electrons moving, right? Where is an electron? Where is this pi electron? There's two pi electrons there, right? Where are they? They're not in a p orbital. They're in a pi orbital, right? Because we take a p orbital from one, a p orbital of the other, we add them together and we get a pi bonding and a pi anti-bonding, right? If you remember, it's going to look something like, this is backwards, by the way, but here's our bonding orbital, right? Here's our anti-bonding orbital. When we drew it on the board, radiating it from lowest energy to highest energy. This was our bonding orbital, right? So that's the one on top. And this is the one on bottom, right? When we put the two electrons in, we fill from lowest to highest via the Aufbau principle. So they go there, right? So for the two pi bonds to interact with one another, all right, we'd have to have so here I've got 1. Okay. Ugh. Okay. And then I've got a second ethylene, right? Because I'm trying to react the two with each other. This is consistent. So for these two to interact with one another, right? Remember, our frontier orbital theory says that electrons from the HOMO of 1 are going to have to interact with electrons from the LUMO of another. Okay? Well, here's my HOMO, right? Or this is my HOMO. You choose either one, they're exactly the same, right? But the interaction that I'm worried about, or that I'm focusing on, is the interaction between this orbital and that orbital. The HOMO of 1 and the LUMO of the other. Well, we've got a problem. This end and this end can interact with one another, right? They have the same symmetry. But what about this end? Does the symmetry of this match the symmetry of that? Doesn't it? And since their symmetries don't match, they can't interact with one another. So this reaction is thermally forbidden. Right? We say it's symmetry forbidden. Right? The reaction cannot happen because the two orbitals don't line up from a symmetry perspective. So thermally, this reaction cannot happen. Is there a way that we could make it happen? There is, right? Because if we move an electron from here to here, and we move an electron from there to there, these two can now interact because they have the same symmetry. They can join together to form one bond. And these two can interact, and they can join together to form one bond. So thermally, it is forbidden, but photochemically, it's allowed. All right? Thermally, it's forbidden. Photochemically, it's allowed. Let's move it on up to what we were just talking about with the 6. If we have 6 electrons, or 6 atoms, yes?
So, how would we, like, I did that, but to get the electrons up, like, how would we decide it?
So it's photochemistry allowed, so you'd have to add light to it. Right? All right. If we take our conjugated system out one more level, okay, we've done the system for 2, we've done the system for 3 real fast. If we're putting in 6 orbitals, how many are we getting out? We're getting out 6, right? The lowest energy one, it's all bonding. We're trying to make them as symmetrical as possible. Yeah. Let's put a time on this or something. Without knowing. 2 nodes there, so 3 nodes are going down, up, down, up, down, up, down, up, down. All right. And again, we're just increasing the number of nodes as we go up from 0 to 5. Okay? And you're just dividing them to get as quickly as possible, or to get as evenly a split as possible. All right? How many electrons are in the system, in this pi system? There's 6, right? The system we're looking at is this, so there's 6 electrons. So we're going to fill from lowest to highest, 1, 2, 3, 4, 5, 6. So our HOMO is going to be this guy. Right? Our HOMO is this one. Here's a question for you. All right, we redrew it, or they redrew it here, so it's already in that kind of cyclic shape. Does this need to rotate in a conrotary fashion or a disrotary fashion for the reaction to occur? Okay, well, you've got the 2 blues up and the 2 reds down. So for them to interact, to get the 2 blues to overlap or to get the 2 reds to overlap, we've got to go in a disrotary fashion. All right? So for a 6 electron system, we've got to rotate disrotary. And if we've got groups on there, when we do the disrotary, that's going to put the groups cis to each other. So by knowing what the HOMO is, and knowing which direction it's going to do, whether it's conrotary or disrotary, it's going to make this so that it is stereo-specific. The electrocyclic reaction in this particular case is stereo-specific. We're not going to get any product from the conrotary. Does that make sense? What about this guy? Would you expect this guy on the top there? Is that conrotary or disrotary? Well, we've got to draw on our HOMO first, right? So HOMO is going to look like that, right? So redraw it. What's your reaction? Does this need to rotate conrotary or disrotary? We've got to get the top and the bottom will be an interaction with them, right? Then this or that bottom. Conrotary. Right? Got to get two both rotating clockwise to each other, right? In the same direction. So whether we're going to do a conrotary or disrotary is going to be determined upon how our orbitals interlock. So for this guy, here's the problem. question you're going to ask is, what kind of a system is this? How many electrons am I moving? 2, 4, 6, 8, 10, 12. Which electrons are involved? And once I figure that out, then I need to figure out what my HOMO is. You know what your HOMO is going to look like. Then you can figure out whether you need to do a con rotary or a disc rotary. Oh. Oh. Here's our 6-electron system, right? So there's our HOMO. So you can think, do I need that to go in the same direction or in the same direction or opposite? So they're both going up, right? Like both of the whites are going up. So to get the whites together, what kind do I need to do? Two groups are both pointed out, both pointed down or out initially. Do my disc rotary, where they're going to go. On the same side, right? So the product's going to look like that. The HOMO? I sure can. Never say always in this class. So we get an overlap. Because initially they're both going out, and then when they do the con rotary, or the disc rotary, they both go in the same direction. Now, yes?
So, since there are 3 double bonds, it's going to be 6.
Mm-hmm.
So the first 3 levels are all 3
Right. Right, so our HOMO is going to be this one.
So that's why it has 2 nodes, or 4 nodes down.
Well, there's a node here, and then there's a node there. All right, so in this one, there's 1 node. Here, there's 2 nodes. Here, there's 3 nodes. Here, there's 4. And here, there's 5. Now, all of this has been from the perspective of our thermochemical reactions. All right? If I react this photochemically, if I put in a frequency of light equal to the gap from here to here, this electron now moves up to there. What's my HOMO now? My HOMO is now this one, right? So it's going to have to go con rotary.
So basically,
All right.
that's the same, going up or down, it is distributed.
Right. So here, when we redraw it, we redraw our HOMO. Now we see we have to go in the con rotary fashion, which means in our product, what's going to happen? It's instead of being cis, we're going to get the trans product.
When there is an even amount of nodes, we said that that's always
No.
on.
I wouldn't do that. No. I'd always just draw it out. Okay. And here you can see a little better picture of what that's looking like. All right. So, another form of an electrocyclic reaction is our Diels-Alder reaction. All right. What's wrong, Colin? Nope, that's not what I had up. Huh? Oh, don't worry about that yet. Yeah. Right. So the Diels-Alder is an electrocyclic reaction. It's a pericyclic reaction. It's electrocyclic because if we look on the left, how many pi bonds do we see? You got 3. How many on the right? 1. On the left, how many sigma bonds are there? 4. And then on the right, there are 6. So from a thermodynamic standpoint, this reaction has a high probability of being favorable because we're switching out a number of 2 pi bonds for 2 sigma bonds. Right? We are going to lose a little bit from an entropy perspective because we're starting with 2 things and making them into 1. But it's a very small change entropically compared to the thermodynamic change. Now, there are 2 parts of the Diels-Alder reaction. The 2 things that we react together are referred to as the diene, which is the molecule that has the 2 double bonds, and the dienophile. Now, what does phile mean? Lover, right? Phileo is love. So a dienophile is something that loves a diene. Right? The diene has a couple of requirements about it as well. It has to be a conjugated diene. They can't be isolated, they can't be accumulated. They have to be conjugated. Now, this is going to be a stereospecific reaction. Since it is pericyclic, note that the 2 groups that are on the same side of the double bond to start with are going to be on the same side of the double bond to finish. Here we have the A and the X on the same side. So the product, the A and the X are going to be on the same side. Now, we will usually form a mixture of enantiomers. Okay? So they'll either both be up or both be down. In a molecule like this, it doesn't matter. But we will usually form a pair of enantiomers. But the groups on the same side are going to be on the same side of the product. Now, the diene itself must be able to adopt the S-cis conformation. Now, what did S-cis mean? When we talk about conjugated systems, we define things as either being S-cis or S-trans. What does S-cis mean? Around a single bond in the middle, or with the pseudo-single bond, we have a cis geometry. Okay? So here, we have the S-trans conformation, because around the single bond, it's sort of trans. And then over here, we have the S-cis conformation. So for the Diels-Alder to happen, we have to be able to adopt the S-cis conformation. Can you draw a molecule, in the narrow sheet of paper, draw a molecule that is a conjugated diene that cannot be S-cis? Draw one that cannot be S-cis. I want you to get an idea of what we're talking about. Double bond cannot be S-cis. would start by drawing something in the S-trans confirmation, and then attaching groups to it that might lock it into that position. I don't think you probably could. Because you can flip this around.
No. Shut up,
Flip this around. Alright. So, let me show you some examples that I saw as I was walking around. One of the ways to think about it is if they were part of some sort of ring system. So if we had something like that, they would be locked into that trans confirmation. I also saw one that was like this. The ring itself is preventing it from rotating here to form that SS confirmation. So neither of these would work in the Diels-Alder. Right? Additionally, you could imagine molecules that were not part of rings, something like this guy. This guy would be inactive in the Diels-Alder. Why would it be, why couldn't this not be SS confirmations? The steric strength. Right? When we try to flip this over, we try to rotate this to get it into the S-cis. We'd have a TBO group here and a TBO group there. We'd be asking those TBO groups to occupy the exact same space. So there's no way that it would get planar to allow the Diels-Alder to occur. Alright? So, the first thing that we say is that the dyne has to be able to adopt this SS confirmation for the Diels-Alder to occur. Now, if we can lock it into the SS confirmation, then it's going to be even faster. One of the fastest reagents out there is actually cyclopentadiene. Now, cyclopentadiene is actually such a good diene for the Diels-Alder reaction that it reacts with itself. In a dimerization process, where the cyclopentadiene reacts with another cyclopentadiene to do a Diels-Alder. Here's 1, 2, 3, 4, 5. There's one of the 5 member rings. Okay? And then here's the other 5 member ring. And so if you go and buy a bottle of cyclopentadiene from Sigma Aldrich, the bottle's going to say cyclopentadiene, and there's not a single molecule of cyclopentadiene in there. Because at room temperature, it dimerizes with itself to form the dicyclopentadiene. So, when you need the cyclopentadiene, you generate it in situ. Notice that this is a reversible reaction. The Diels-Alder reaction is a reversible reaction. And so if you heat this up to 170 degrees Celsius, you're at a high enough temperature so that the starting material becomes favorable. You break up the dimer and turn it back to the cyclopentadienes. So if you need cyclopentadiene for a reaction, you start by putting in the liquid, refluxing it, getting it heated up to 170 degrees, and then add in your other materials so that to get the reaction you desire. Now, what's great about this from the perspective of the Diels-Alder is it means that this reaction will form bicyclos pretty easily. And it's really, as far as we're concerned in this class, it is the best way to form a bicyclo. If you've got a bicyclo on a synthesis problem, the first thing I would always look to do is to say, can I make this from a Diels-Alder? Because I would say 8 or 9 out of 10 times, bicyclos are made easiest using the Diels-Alder. So that would always be the first place I check. Okay. Now, there are certain things that are going to make the reaction go faster or slower. All right? There are certain things that we can do to make this reaction speed up or slow down. For example, if we take 1,3-butadiene and react it with 3-butene-2-O, this reaction will occur at 140 degrees Celsius. All right? We always use as an example 1,3-butadiene reacting with ethylene as our Diels-Alder of choice. That reaction is really hard to do. When we're talking temperatures, usually over 300 degrees to get that reaction to work. But if you put an electron withdrawing group on the dienophile, electron withdrawing on the dienophile, it speeds the reaction up. So if an electron withdrawing group speeds up the reaction, if it's on the dienophile, what kind of group do you think is going to speed it up if it's on the diene? We want an electron withdrawing in the dienophile. What kind of, right, for the diene, we'd want an electron donating group. Right? For the dienophile, we want electron withdrawing. For the diene, we want an electron donating. Which obviously begs the question, why? But we're going to have to wait till Friday to figure out. I will see you then.